If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Please share it with all others who might benefit. Let's get started. In this video, we're going to solve a real-world classification problem that's a joint application of Internet of Things and artificial intelligence. This problem is about smoke detectors. We know that smoke detectors are crucial for early fire detection, which helps provide a rapid alert system that can save lives and prevent property damages. So this dataset has been obtained from the very popular site called Kaggle and is attributed to Stephen Blattman. This is a very detailed article which talks about smoke detectors and how smoke detectors work and everything to a great detail. I highly encourage that you go through this article, as the link to this article and the related dataset will be provided to you in the description of this video. But to come back to the case study, let's understand the importance of this case study. We know a smoke detector is important for saving lives, but what's the kind of impact that smoke detectors have been able to bring? So it is estimated that about 48% of decline in the fatalities in France between 1982 to 2012 was primarily attributed to the presence of smoke detectors. That number is about 56% for United Kingdom. And if we talk about US, 96% of the households have smoke alarms and approximately 20% of homes with smoke alarms have non-operational smoke alarms, which could be dangerous. It is estimated that if every home had a working smoke alarm in US, residential fire deaths could drop by 36%, which corresponds to about 1,100 lives saved per year. That's a huge number. So this case study becomes really important because it has a direct connection with saving lives. Let's look at the kind of variables we have. So we have a timestamp variable, which is UTC. We have a variable called air temperature, air humidity, total volatile organic compounds measured in parts per billion, CO2 equivalent concentration, raw molecular hydrogen, raw ethanol, air pressure, particulate matter 1 and 2.5, and number concentration of these particulate matter, the sample counter, and finally the target column, which is 0 or 1. It's a binary class column. Ground truth is 1 if the fire is there. When it's not the case, it's marked as 0. So now let's move on to this case study. We begin by importing the basic libraries like NumPy and Pandas, and then we read this data set, for which the link is already present in the description, using the read CSV method, because this is a CSV file. If you look at the first few observations of the data, we have columns like unnamed, so this is going to be a useless column. Then we have all the columns relevant to the variables as described above, including the last column, which is the target column, a 0 or 1 kind of a column. So we can drop the columns that we are not going to use. So we're dropping the column called unnamed, which in any case does not contain any information. We're dropping the column called sample counter or CNT, because this is just a sample counter, kind of a serial number column. And we are also dropping UTC. While there may be some relevance to the timestamp, but we are more interested in seeing the influence of the other variables on the target. So we, in this case, choose to drop the variable called UTC, and we'll proceed with that. Please note this data sample would have been collected at different times and different environments. For example, it could be indoor, outdoor, it could be under high humidity, high temperature, and different kind of fire influences as well. It could be a gas fire or a wood fire that would lead to different outcomes. So normally such data sets are collected under varying conditions. And that's what we will be more interested in studying compared to just studying the timestamp. Let's check the shape of the data frame. So the dataset has about 62,630 rows and 13 features. If we want to get the general information about the dataset, which would tell us about the nature of the variables and if we have missing values, etc. So it looks like all the cells are occupied because we have 62,630 rows and we don't see anything missing here in terms of non-null entries, which means all the cells are properly occupied. Also, we see that this data set is entirely numerical because all the features that we have are either floats or ints. Now, we are just checking the instances of fire alarm in our data set, 1 versus 0. So 1 is a fire alarm case when there is a fire, and 0 is the case when there is no fire. So let's just check that. So this is the breakup, and if we want to divide it in percentages, we can do normalize is equal to true and multiply with 100. Essentially, 71.5% cases approximately represent the incident of fire, and 28% cases represent the case of no fire. Now, we first begin by splitting the data set because we'd want to park some data for validation from a future perspective, and we'd want to use a larger chunk of the data for preparing a model. So in this case, we are first separating X and Y. From the X variables, we are just excluding the target column, and Y variable is the fire alarm itself. And we are doing an 80-20 split. 80% of the data goes to training, and 20% of the data will be parked for test. Let's do that. Now, if we check the shape of the train and test set, this is how these sets are. About 50,000 rows in training and 12,500 rows in test. We begin by checking the presence of missing values in our train and test data set. We in a way already saw this through the info. We don't have missing values in train or test. So we're clear about this. Let's check the presence of any duplicate records. And this is something that we do by using the pandas.duplicated method. We are printing the sum of total duplicate values. We seem to have 2 duplicate values, but that would not make much of a difference in our overall analysis because the data set is quite large. We are talking about a train set about 50,000 observations. At that kind of a base, just 2 records being duplicate would not make much of a difference. Now we are checking the presence of outliers, and the easiest way to detect the presence of outliers is through the box plots. Since the entire data set is numerical, rather than creating box plots for one variable at a time, we will smartly create box plot using a proper loop. So what we're doing is we are setting up a figure size as per matplotlib, and we are creating a list of features as we have in the training data. So to a data frame, when we do dot columns that returns a list of all the features, this will be called a feature list. And then we will go over this feature list one at a time to continue to create the box plots. We are saying we will run a for loop for I in the range over the length of all the features. Xtrain.columns is a list. So length of that list would be nothing but the count of the number of features. And we will go over each single feature, creating a plot for it. For this, since we have 12 variables as we saw earlier, we'll be dividing a plotting area into 4 rows and 3 columns. That will be sufficient for placing 12 plots. And then we are using index I+1 to indicate the index of the plot. We create box plots and dynamically update the titles as per the name of the feature. So when we say feature list, index I, this I is going to take values from 0 up to the length of this list -1. 0 to n-1. If we have 12 features, it'll take values from 0 to 11 because indexing in Python works from 0. It'll show the box plots for all the features. So as this finishes running, we can see that a lot of features here seem to have outliers. Temperature, humidity, TVOC, parts per billion, all these features have significant amount of outliers present. Since the logistic regression model that we are going to apply in this case is sensitive to the presence of outliers, we will go about treating the outliers. How do we treat the outliers? First, we will calculate the upper and lower limit for all the features in the trained data. And then we will calculate the IQR or the interquartile range, which is nothing but the difference of the 75th percentile and the 25th percentile for all the variables. Then we are defining a function which will take the input as the name of the data frame and each feature. It will calculate the lower bound and the upper bound for each feature. Lower bound is the value below which a value is an outlier. Upper bound is the value above which a value in the data is considered an outlier. And generally, the definitions for these are Q1 minus 1.5 IQR for the lower bound and Q3 plus 1.5 IQR for the upper bound. Within this function, what we are doing then is we are applying a method called np.clip, where we are giving the specific column, and then we are telling if a given value is below the lower bound, we must bring it to the lower bound. And if the value is above the upper bound, we must bring it to the upper bound. So this is called winsorization. This will take care of the outlier treatment for all the features. Finally, we are saying for each column in xtrain.columns, we are applying the street outliers function that we have defined here. Here we have provided a short note on how np.clip works. In a way, I've already explained that. Now let's recheck if we still have outliers. Exact same code that we ran some time back, but then we had outliers. Now that we've applied the street outliers to the trained data, let's see what's the current state. And now you see the outliers have been removed. We don't see the presence of outliers as we had earlier. Now, based on the quantiles that we found here in the training data, we are going to train the test data as well. For the test data, we do not do separate outlier treatment. We don't determine the upper limit, lower limit again. We are calling the same function we defined above directly on the test data, and it will modify the test data as per the boundaries found in the trained data. And if we check the presence of outliers in the test data now, we have just some borderline cases, but by and large, the outliers have been treated. Exceptions are there for a few features, but more or less, the outliers are minimal in case of test data already. It's not as bad a situation as we had to begin with in case of trained data. Now we may want to check if the features are correlated. And now we'll have to be a little patient with this particular code because it does take a lot of time. So we are doing a pair plot first to check if the variables that we have in our data have a linear association or not. Because only when the variables have a linear association is when studying the correlations makes sense. Pair plot is going to create various scatter plots with the paired variables The diagonal of this pair plot would show individual histograms for each variable. And this is usually a slow code, so it does take some time. You'll have to bear with it. Okay, so we finally have the pair plot. As you can see, it doesn't look very pleasant because it has all sort of patterns here. Essentially, these are all, the off-diagonal elements are all these scatter plots pairing every possible combination of variables. But if you see it here in this specific section, you do find a lot of linear relationships. And that's kind of natural. If you go through the feature description, you would find there are certain features which may have some connections. For example, when we talk about the particulate matter and we talk about its concentration, there may be a relationship, right? So we have some features which exhibit a strong linear relationship. And like I said, very important is that we study the correlations only if the linear relationship is confirmed. So let's go ahead and at least now we can interpret the correlation meaningfully. So what we are doing is we are creating a heat map to which we are giving the input as the correlation matrix, the train data correlation matrix. We are doing some customizations, like we are displaying the values in the correlation matrix. We are choosing a color scheme which is cool warm, so it's kind of shades of blues and reds. And we are showing all these values, annotated values, in 2 decimal places. Generally, with the color coding, it also displays a color bar, which should take values between a -1 to 1, because that's how the correlation coefficient is supposed to be. It's supposed to always range between a -1 to 1, and we're giving it a title. So let's run this. This will be fast, and we will be able to see the value. So we do not seem to have a lot of strong correlations everywhere else, but these correlations here. And if you see, this pretty much corresponds to the kind of relationship we had here between the variables. So there's a very strong linear relationship. It's almost to the extent of 1 or 0.94 or 0.95. Pretty strong positive correlation between certain variables. Now, logistic regression model is again very sensitive to correlations. We know that. So we will have to treat multicollinearity, for which we choose to apply the variance inflation factor. Now, this code may be a little complex for people who are new to this. So just pay attention and you'll be able to follow what's happening. First of all, we are defining an empty data frame, which does not have anything to begin with. It's just a pd.data frame and nothing inside. Then we are adding a feature to this data frame, which is called feature. It will be the name of the feature. These are the columns that we get from the train set. And we are adding a feature which will capture the VIF value. So this is the name of the data frame, lowercase VIF, which has 2 columns, feature and VIF. Now, this VIF is something that we can very conveniently calculate using this VIF class that we get from statsmodel stats outlier influence module. So what we are saying is that for each I in the range of the X train shape 1, so shape 1 refers to the columns of X train. We are going over each column, and what we are doing is we are calculating the VIF value using this particular class, VIF variance inflation factor class, which requires the input as the X train dot values and the index. And then sorting the VIF values in a descending order, because we are supposed to identify the variables with the highest VIF. And in that order, we continue to eliminate these variables. So let's just print this out and we'll get an idea of how the VIF is. So VIF is extremely, extremely high. So if you've watched a video on multicollinearity, you would know generally a VIF of greater than 5 is considered alarming. And we have a lot of variables here. In fact, just one variable is such which has a VIF less than 5. But the tricky part is that we cannot drop all the variables with VIF greater than 5 at once. We continue to drop these iteratively. So first we'll pick the variable with the highest VIF, we'll drop it, then we'll revisit this entire piece. Again, look at if there is a variable greater than VIF 5, we drop it, and we continue to repeat this. So we repeat this process multiple times. There are times when people follow a VIF threshold of 5, there are times when they follow a VIF threshold of 10. In our case right now, we'll refer to the VIF threshold of 5. Now, in order to do this conveniently, we are going to use a while loop. While we have lesser number of features, let's say about 12 features, we can do it one at a time also, and we'll be fine by repeating the same code about 7-8 times. But if we have larger number of features, it will not be advisable that you do it manually. The loops will come for our assistance. And which loop are we supposed to use in this case? So we'll be using a while loop, because we don't exactly know how many times we are going to repeat this exercise. We'll continue to drop the variables till we reach a stage when the VIF is less than 5. So what we are doing here is we are defining our VIF threshold, which is max VIF of 5. We are creating an empty list which will collect the removed variables, and we are setting a flag which is true. So while loop will require a condition. If that's true, then the loop starts, right? So we are saying till this condition is true, we will continue to run. These 3 lines are exactly the same as we did here. The VIF data frame, the feature, and VIF thing. Because we have to do this repeatedly, then we are saying that we want to capture the variable which has the highest VIF value. So VIF data frames, VIF column, and IDX max. So this IDX max returns the index of the feature with maximum value. We are referring to that feature which has the maximum VIF value, and we are using VIF.lock. Now, if you know, lock is something that's used to access the information in a data frame. So when we find out the maximum VIF value for a given feature in the VIF column, if that is greater than the threshold that we've given, which is the max permissible VIF, then we are going to remove that feature. So I repeat, for a given feature, if the VIF value is greater than the threshold, we are going to remove that feature. We are putting it as a removed variable, and we are going to drop that feature with access is equal to 1 from the training data. We are appending that variable, however, to the removed variables list, which we'll be using later. So two things that we are doing here, we are dropping the feature from the data frame, and we are adding the variable name to a list here, which is a separate collection that we are populating. Now, this is within a while loop, and within this loop, till the time this condition continues to be true, we will keep on dropping such variables and keep on appending them to the list of removable variables. But if this condition is false, which means you no longer have any variable that has a VIF value greater than the threshold. If that's the case, we come to else and we change the flag to false. The moment we change the flag to false, this while loop terminates, because this while loop will execute only if this condition is true. If we run this and finally look at the features, it will continue to display the name of the features that we are dropping at all stages, and it will continue to display its VIF value. And finally, we are also printing the list of features that we are left with after removing all the unnecessary variables. So if we scroll down, this is the output. The output says we have removed the variable with high VIF, TM 1.0, the VIF was this much, so on and so forth. All of these have been removed iteratively. And finally, we are left with just 3 variables. So we started with 12 variables. Now we only have 3 variables. These are the 3 variables that we are going to use for our model. Now, for the test data, we are going to drop these variables straight away. We don't have to check the VIF there separately because test data is equivalent to future data. We may not want to do a lot of analysis there, but we will carry forward whatever we learn on our trained data to the test data. So we are just dropping those variables directly in the test data. That's the reason we created a list there called removed variables, which kept on appending all the variables, these variables that we were going to drop. And now we just run it. Let's check the shape of the trained data and let's check the shape of the test data. This is how the data is. Only 3 features. The number of rows are pretty much intact. Let's check the head of the data. So you see that the variables are on different scales. Now, if you're using logistic regression and you would want to interpret the coefficients, then you might want to scale the features. Moreover, scaling also makes the algorithms converge faster. So for that purpose, you may use it, though it is not strictly mandatory for regression problems. So we are using the standard scaler. We can conveniently use this because we do not have outliers in our data anymore. We can call the standard scaler from scikit-learn preprocessing and do a fit transform on the trained data and a transform on the test data. Remember, whenever you do some preprocessing through any library, you'll always be doing a fit transform on train and transform on test. What is the difference? This fit method essentially calculates the mean and standard deviation of the trained data. And transform method applies that x minus mu by sigma transformation on the data, which is a z transformation. For the test data, you don't want to calculate the mean and standard deviation because test data is equivalent to the future data. So whatever is the mean or standard deviation that you capture from the trained data would be used to apply transformation to the test data. This is the reason for train we do a fit transform and for test we do only transform. When you apply this fit transform, your data would generally be converted into an array. So to store it back in the form of a data frame, you'll have to pass this entire piece to the pd.data frame. Now arrays would not have columns, so we'll have to mention the column names again. That's why we are doing this. So we're getting xtrain scaled and xtest scaled. And now we proceed to the model building. Here we are calling the logistic regression class from the scikit-learn linear model module, and we are calling a couple of evaluation metrics from the scikit-learn metrics module. These are called confusion matrix and classification report. So we are instantiating the logistic regression model with a certain random state just for reproducibility, and we are doing a fit of the scaled train data and y-train as we had. Now, since we scale the data, we are passing the scale data now, and then we are also passing the y variable because this is where the model will learn. The model will be fitting. Once the model is fit, we are generating our predictions both on train as well as test. Again, we are passing the input as the scaled data. And once the predictions are generated on train and test, we are evaluating the model using the confusion matrix, passing the input as the actual or the ground truth label and the predictions, both for train and test. So this is a pretty standard process that we'll be doing for all the models. Once this is done, we've stored the confusion matrix already as an object. We can try to plot this. So just to make it appear nice, we are going to pass this confusion matrix to a heat map, which will be more of a color-coded output, and we are giving it proper titles and labels. We have divided the plotting area into two parts. So we'll have one row and two columns. First would be the performance on the training data. Second would be the performance on the test data. Here is the outcome. So if you know how to read the confusion matrix, this box represents the true positives. This box represents the true negative. This represents the false positive, and this represents the false negative. We have the same output available on the test data as well. So let's quickly understand what these values are. True positives are the values which are the instances where the model correctly predicted a positive class, a fire alarm when the ground truth label was also positive. So when it was actually a fire, the fire alarm worked, is what we can say here. True negatives are the cases where the model correctly predicted a negative class. No fire alarm when the ground truth level was also negative. So there was no fire and there was no fire alarm. False positives in our case represent the scenarios where the model incorrectly predicted a positive class, which means it's a false alarm when the actual class was negative. And the false negatives are the instances where the model incorrectly predicted a negative class, that is no fire alarm when the actual class was positive, which means there was a fire. So one thing that you have to always keep in mind when you're working on any data is, what is the priority? A false positive here is a case where the fire alarm triggers an alert when there is no fire. That's bad, but that's not a threat to life. But false negative is a case where the alarm didn't trigger and actually there was a fire. Isn't this worse? Isn't this dangerous? So keeping these two things in mind as to what has a higher severity, you may prioritize your performance metric. While we'll be looking at an overall output here because this is one of the first case studies, it is important to have this understanding so that you are able to prioritize the right model performance measure. False negative features in the definition of recall, which is true positive divided by true positives plus false negative. False positives features in the definition of precision, which is true positive divided by true positives plus false positives. So if you're saying that false negatives are more critical for you because these could be hazardous, then recall becomes your priority metric. But if you're more bothered about the false alarms because that's how your firefighters are dispatched to a location and they start doing their work, and if there are so many false alarms, they will be unnecessarily reaching out to locations where they're not genuinely required, then maybe precision is your priority. So we'll look at both. We will print out the classification report for the train data and test data and compare. So here's the classification report. See, 92% of recall for once means that out of 100 actual fire incidents, in 92 cases, there were a proper fire alarm triggered. And whenever the fire alarm triggered, 78 out of 100 times, it was right. This is precision. So we don't have a problem here with ones. This seems to be doing good. But we may have some concern with the zeros. So zeros are the cases in the ground truth data where there was no fire. So this 0.35, which is the recall for zero, what does it mean? Out of the total no fire incidents, how many were identified correctly by the model? 35 were identified correctly. It means 65 incidents of no fire were not identified correctly by the model, which is bad. And the precision of 63% means that whenever the models predicted a zero, it was right 63 out of 100 times. So it identified very less, but whenever it identified, it was right roughly 2/3 of the times. This is one area of opportunity that we have with the current model. And in our subsequent tutorials, we'll learn how to deal with such situations. There are multiple ways to deal with it, including trying different models and including different techniques to data preparation. And if you look at the test data, the performance is totally consistent. It's pretty much the same. Your values are almost identical in the test data. So train and test performance is pretty much in sync. We don't have a problem. As far as the class 1 is concerned, the actual detection of fire is concerned, the model seems to be doing excellent. There is a scope of improvement as far as the non-fire incidents are concerned. So this is how we can compare the performance of the model during the training and test set, and which is where we see fair amount of consistency. We did this entire exercise using the logistic regression class from scikit-learn model, which is super popular. But there's another way to do logistic regression in Python, and that's using the statsmodel library. Why I'm talking about it in particular is because the output of this library is very detailed. So you may want to have a look at it as an alternative. So what we're doing here is we are importing the stats model API as SM. This is kind of an alias. And then we are passing the scaled train and test data to this method called add constant. Now, stats model has a slightly different style of working. It doesn't by default include the intercept or the constant term in the model. So if we want to include that, we have to specifically add it using the add constant. This is the same scale data that we obtained above. And we are saying this would lead us to the X train for the stats model and X test for the stats model. Now, stats model, as I said, works in a slightly different way. So it does try to map the indices of X and Y, which is fair. But what has happened is when we scaled the data above, we would have affected the indices. Because when we scaled the data, we had to convert it back to a data frame sometime back, and that would have realigned the indices. In order to ensure that Y variables also have the same indices, we are doing a reset index on the Y variable. This drop is equal to true ensures that the index column is not a part of the data frame, is treated as index separately. Applying reset index on the original Y train and Y test, we obtain the Y train for stats model and Y test for stat model. Then to the logistic regression model, we pass this as the input, Y train and X train, and then we do a fit. Finally, when we do a results.summary, it comes with a very detailed summary. Now, it may not be totally useful for us because it gives a lot of additional information. But if you can see, it gives you the coefficients of the variables, it gives you the p-value of all the features, and also a confidence band around the outcome. Now, can we get the coefficients through the logistic regression and scikit-learn as well? Answer is yes. We have attributes like coef underscore and intercept underscore. So this is the name of the logistic regression model we had from the scikit-learn library. We are comparing the coefficients of this model with the output that we're getting from stats model, and you'll see there are a lot of similarities. For example, the intercept here is 1.097, and in case of scikit-learn also it was 1.097. The coefficient of the first variable temperature is negative 0.5664. It's again pretty close, negative 0.5662. The coefficient of the second variable is 0.6082 in case of scikit-learn. In case of stats model, it's 0.6083. The third variable is 0.440. And this is again nearly same. So there's a slight difference in the calculations, the way they approach in terms of regularization and the other workings of both the libraries. But if you see, the results are fairly comparable. And in order to generate the confusion matrix using the stats model library, we have a slightly different approach. So we do a dot predict here as well to the result. So what is the result? Result is nothing but the fitted model that we have. To the result, we call dot predict. We pass the X train SM, which is the stats model ready train data. And when we do this dot predict, it does not return the class, it returns the probabilities. So to convert the probability to the class, we compare it with the threshold of 0.5. If it's greater than or equal to 0.5, it's converted to a 1. Otherwise, it's converted to a 0. Similarly, for the test data, when we get an outcome which is greater than 0.5, that will be converted to 1. Else, that will remain a false, and that will be converted to a 0 by doing as type int. So finally, we do a classification report exactly the same way as we did for the previous model. Let's look at this outcome. So if you see, these values here that we got here are identical to what we were getting here in case of the scikit-learn model. At times, there could be a slight difference in the results, but that's not significant. So this is another quick way to do the model using the stats model library. So coming back to the key takeaways from this case study, first of all, this was a real-world data set. And we know how important it could be for a fire alarm to trigger when there is actually an incident of fire. In this specific case study, we learned about how to deal with outliers through a basic technique, upper limit and lower limit. And we learned about how to deal with multicollinearity. To start with, we had 12 features. We were able to cut them down to 3 features. And still a model for a fire detection gave a 92% recall. This still has some opportunities, like the recall for class 0 is not great. Now, this is where we may at times have to focus on the domain. So notice, when would these values be unusual? Of course, in case of fire, the temperature would rise, the humidity might increase, the other gases and particulate matter might be on extremes. So when we treat outliers just to suit our model, because logistic regression is sensitive to outliers, we treated the outliers. We, in a way, affected the model's ability to decipher between a 0 and 1. In future, we will try to use the same data and solve this problem using other models which are not as sensitive towards outliers. In fact, you can take that up as an exercise for yourselves What if we choose a model which is not very sensitive to outliers and then pass this data? How would the confusion matrix look like? Well, that's all for now. Hope you had something new to learn. Thank you.